Alright, on this set of notes, we're going to do applications of exponential growth, but on these applications, the growth constant will not be given to us. We actually have to find it. Alright, so this is an example of, suppose in 2009, the U.S. per capita income was $48,040. By 2012, the per capita income grew to $52,430. Assume the personal income in the U.S. per capita follows an exponential growth. All right, the starting year is our initial year times 0. Find the exponential function for the income in terms of the number of years after 2009. Round our k 4 decimal places. So I've got to remember to do that. And then we'll use it once we find our equation. So these are going to be applications where we have to find the exponential function, set it up, find k, and then once we find it, we'll use it. Alright, so first we have to find k. Alright, the percent at which the population is growing. And so they gave us two values. They gave us the initial value, so I'm going to let I of t represent, again, it's exponential growth. They told us that. So I of t, I naught e raised to the kt. I naught they give us, that's the initial year, which is 2009, which was $48,040. Alright, so we know the initial year. Then they gave us this other piece of information. They said by 2012, which would be, so 2012, which would be time 3, right? It's 3 years after 2009. So at time 3, our income was $52,430. And so this is the piece of information I'm going to use. These are the piece of information I'm going to use in order to find our exponential function. All right, so remember, I talked about this in the earlier set when we first were setting this up. You can either remember that quick equation if you want to for k. So remember, k is the natural log of my quantity at times t over my initial quantity over the time. And so for this particular application, that would be, our quantity at time t would be the 52,430 divided by our initial quantity, which is the 48,040, all over the time it took us to grow to that 52, which was 3. All right, and then the k value would be, rounding 4 decimal places, 0.0291 if I round 4 decimal places. All right, so that's one way you can remember that, which again, we talked about that in the first set of the first video for this set of notes. If you don't want to do that, what you can do is plug the information into this equation. So an alternative to memorizing that equation, I know that after 3 years, my quantity grew to 52,430. So I set my equation equal to the 52,430, plug in my initial value, the 48040, e raised to the growth constant, which is what I'm looking for, times the time I was given, which was 3, right? It took 3 years to grow to that amount, and then you solve for k. All right, divide by the initial value. And so I'm just going to leave the fraction. If you want to simplify it, you can, but don't round it. All right, either leave it exact or simplify it. You could simplify it, plug it in your calculator, and hit the fraction key if you wanted to. All right, and so I got this fraction on this side. I'm taking the natural log, and then I basically get down to that expression. All right, my next step would be dividing by 3, and I get to this expression. When I get to that expression, I get to my k value. All right, so again, it's up to you. Whichever way you want to do it, you can. You can either remember this or set it up. Alright, so once we've done that, now we found our k, and so I've got my equation, and now I just have to write it in the equation format, and once I've got my equation, I can do the rest of the problem, once I found k. Alright, so give me a second. Well, I erase this and give myself more room to work. Alright. Alright, so the answer to A is my income at times t is equal to the initial value, which is the 48,040, e raised to the k that I just found, 0.029, which I rounded 4 decimal places. Make sure you round that. If they say 4 decimal places, round 4 decimal places. If you round 2, 3, or 1, you'll get a different answer. All right, so because it's exponential, the rounding error will be significant. So round exactly to what the problem says round to. All right, now we're just going to use it. So here's my equation. So there's part A, and now we're going to use it. So the first question is predict the U.S. per capita income in 2020. All right, so 2020 would be 11 years after 2009. And so we're going to plug 11 into that formula. And since it's money, I usually round money to the penny. All right, so it's dollars, right? So make sure I put my units. So when I plug it in, it comes out $66,163.83. So there's the answer to B. All right, the last question, part C, is when will the income double, right? From our starting year, right, 2009. So after 2009, when will we have twice this 48,000? All right, so again, there are 2 ways you can do that. You can remember that doubling formula. My doubling time is equal to the natural log of 2 divided by k. So in this case, it'd be the natural log of 2 over that 0.0291, which comes out to be, if I plug that in, 23.82 years. All right, so it'd take almost 24 years to double. All right, so again, 28 years to double. If you don't remember that, you could set up the equation where you double the 48,000 and solve it that way, where you could write, 2 times my 48, 40 equals my 48, 40 e raised to that k that we found, times my doubling time. And then solve for your doubling time. If you do, right, this will divide out. And so here I'll be left with 2. So I'm going to write it over here. Equals the e raised to the k times my doubling time. And then we'll take the natural log. And again, we'll get down to the natural log of 2 equals my 0.0291 times time. And then the last step would be divide by that 0.291. 0.291. Alright, so we get to the same thing, which would give you the same answer that I found above. So again, it's up to you. If you remember this quick equation, that's the faster way to do it. But if you forget, you could always set it up and solve. You'll get to the same answer either way. Alright, so the next example. Alright, so that was a general case where they gave me a general number, and we had to find k. This one, we're given our double time. Right? Suppose the population of a certain town is growing exponentially. On January 1st of 1970, the population of the town was 10,000 people. The town's population doubled in 25 years. All right, so we're given a doubling time. All right? Determine the function qt that represents the town's population in thousands of people as a function of time. All right, where time t is when we start. Our initial time is 1970. This time we're going to round the growth constant, to 3 decimal places. So I've got to remember that when we get to the k part. All right, so A, set up our equation. Our quantity represents our population, q naught e raised to the k times time. All right, so our q naught was the year 1970 is where we're starting. 10,000 people. So I'm going to leave it 10, and I'm just going to leave this in thousands of people. All right, if you want to write out 10,000, 10, with 4 zeros after, you can. Then they gave me my doubling time. Doubled in 25 years. All right, which again, I can use my doubling time shortcut formula if I want to. All right, my constant is the natural log of 2 dividing by my doubling time. Right, that's that quick formula that I talked about at the start of this. And then you plug that in the calculator and round 3 decimal places. So it rounds to 0.028. All right, that's one way you can find the constant. Or, again, I know my quantity, when I plug 25 into it, it'll be twice what I started with, so I'll be at 20,000. Take 20,000, set it equal to my 10,000, my initial value, e raised to the k times my doubling time, which is 25, and then solve. All right, when you solve that, it should simplify down to, right, you'll divide by 10, that's where the 2 will come from. Take the natural log, so it'll be the natural log of 2, and then divide by the constant. So again, oops, not 2. You'll divide by the 10, which you'll get 2e to the k times 25. You'll take the natural log. Those will cancel, and so you're going to get the natural log of 2 equals k times 25, and then the last step would be divide by our 25. All right, and that'll give you the same answer we got there. All right, so again, you pick your method, whichever one makes the most sense to you. All right, so now I've got everything that I need to answer part A. All right, so my population, which is what Q of T stands for, is equal to my initial population, 10,000, e raised to the 0.028 times time. And again, I'm leaving it like this. If you want to write 10,000 out, you can. Since I'm leaving like this, I have to remember it's in thousands. If you prefer, you could write out 10,000 e to that k times time. And again, it's just up to you however you want to do it. All right. So, part B. Right, what's the town's population in 1985? So 1985 would be 15 years, right, after 1970, right? 1970 is our initial year. And so I take the equation we found in part A and plug 15 into it. All right, remember mine, I have to remember my units on it are 1,000. So I'm going to round a couple of decimal places, so I get 15.2196, but I've got to remember it's in thousands of people. And so they have about, if I round, 15,220 people in 1985. All right. Part C, at what rate? All right, so this one's asking for a derivative, which we actually haven't really done a derivative of these problems because the first set that we did, we were given the derivative. And then the last problem I didn't ask it. So this is actually the first one where we're asking you to find the derivative. And so we're asking for a rate, which means the derivative. So I need to find my derivative at 1980, which would be time 10. Right, I plug 10 in to my derivative. All right, so the derivative, remember for exponentials, is pretty straightforward. First thing you write down is the original function, 10e to the 0.028 times time, but then you're not done. Remember, we always multiply these by k. All right, that's the derivative of these. All right, I'll probably simplify that. So I'll multiply, so that's going to move my decimal place over. So 0.28 e to the 0.028 times time, and then plug in my 10. All right, so we've got all right, so give me a second. Oops. Comes out 0.3704. Remember, it's in thousands of people. I left mine in thousands. All right, thousands of people per year. All right, rate of change would be per year. All right, so I'm going to clean that up a little bit and write up here. So the population is growing by about, since I'm going to round, 370 people per year in 1980. All right, so remember, derivative is always a rate of change. So you've got to write it with the rate of change, like miles per hour. All right, how is it changing? What's its speed? In this case, the population is increasing by people per year. All right, and either thousands of people per year if I leave it as the decimal, or I just multiply by 1,000 and wrote it as 137 people per year instead of in thousands. All right, so there's the answer to the part C, the last part of that question. All right, so the next set of notes is still exponential growth, but it's looking at a special type of exponential growth, which is specific to money growing. All right, so it's the same equation. This is the exact same equation. B of t would be my function. P naught would be my initial value. The difference is we're putting it in terms of money. All right, but it's the same equation, the same application types that we just did. The difference here is again, everything is in terms of money. All right, so when we say money is growing continuously, right, which we say continuously compounded in interest, that means our money is growing exponentially. All right, and so it follows this. Like a lot of times, again, if you've ever seen this, they say this is the Pert equation, right, because it kind of spells out Pert. It's the exponential growth equation, all right, where the function is the future value after t years, how much your investment is worth after t years. P naught is the present value of the investment, so how much you invested at time 0 when you put your money in the investment. R is your annual interest rate as a decimal. Well, R is just the money represent continuously compounded interest. Well, the interest is telling you how fast your money is growing. It's growing by a percent, right? The percent at which your money is growing. Well, that's K, all right? That's the K that we had in the previous problem, the percent at which your money is growing. In this case, we call it R because in money terms, in financial terms, the way money grows is in terms of interest rates. And for interest rates, it's always annual. It's always per year. Money's always going to grow per year, annual interest rate. And so time for these is always in years. All right, money is growing yearly. All right, so again, it's the same equation, just in terms of money. All right, so we're going to be using the Pert equation. All right, so remember, interest rate is just K. For this problem, if an investment of 5,000, so 5,000 would be how much we invested, that's our principal, P naught, all right, so this is our initial amount. This would be a future value, right? In 5 years, it grew to 7,000, so that would be a future amount, and it took 5 years to grow there. It's compounding continuously, means it follows this exponential growth equation. What's the interest rate? Round 3 decimal places. And then what's the value of the investment? So we're going to use it. So first thing, we're going to find this equation, and then we're going to use it. All right, so they gave us the initial amount. We started with 5,000. They told us that in 5 years, so the future value, so 5 years, the future value grew to 7,000. So again, this is where we're looking for R. Remember, R is just the K in financial terms. All right, it's the same, works the same way as K did in all of our previous examples. So there's 2 ways you can do this. You can either remember that equation, it's the natural log of my future value, my future amount, divided by my present amount, all over the time it took us to grow there, which was 5. Or you could set it up. All right, so again, you could plug these into that equation. I know that I'm going to grow to 7, my future value is going to be 7,000. That's going to equal my present value, 5,000, e raised to my interest rate times the 5 years it took us to grow to that 7,000, and then solve for R. And so the first step would be to divide out my 5,000, which actually I can simplify that. My zeros all cancel out and leave me with 7 over 5. Equals e raised to my interest rate times time. Take the natural log. And so on this side, I get the natural log of 7/5 equals my interest rate times 5, divide by my 5, and that will give me the same interest rate as this value. All right, so both of these should come out exactly the same. All right, so when you do that, round 3 decimal place, got to remember how, because again, you want to, if you round differently than what they say, your answers will be significantly off. You'll have a rounding error, and you don't want rounding error. All right, so if you plug that in, it comes out to 0.067. So either way you do this, you should get an interest rate. Again, it's a growth constant. It means my money is growing. The investment is growing at a rate, excuse me, of 6.7% per year, right? Because it's annual. All right, so that's the relative percent growth rate. That's K. All right, so I found our interest rate, R. All right, now we're going to, in part B, use it. All right, use our interest rate and solve for how much money, what will be the future value in 10 years. So first thing I'm going to do is write my equation. My future value equals my initial amount, which is 5,000. E raised to my interest rate I just found, 0.67 times any time, right? So this allows me to find any time. Well, we asked it for 10 years, so I'm going to plug 10 into this equation. So I plug 10 in. Again, it's money. I typically round money to the penny. So first of all, $, that's the units on it. And so in 10 years, my 5,000 will almost double, not quite. It goes to $9,771.19. All right, and so that's how much money he'll have in his account in 10 years. All right, the last question for this video set and for this set of problems. All right, this is actually a problem from your book. It's problem number 14. And this one's sort of we know Hardy Bake advertises that they'll have compounding interest. So if you invest with them, they're going to compound your interest, and they guarantee that it will double your money in 12 years. What's the annual interest rate? And so this is using that doubling time formula. R really is your K value. It's just in terms of money. And so the doubling time is the natural log of 2, because it's doubling, over the doubling time, right? So that would be the interest rate. So you take the natural log of 2, divide by 12, and it comes out 0.0578 if I round forward. And they didn't tell me how much to round it to, but this would be the value, right? And so that's using that short formula, that doubling time formula, right? So my interest rate would be that amount. You could set it up in case you forgot that. You could just make a generic amount. My present value is some amount. We know that my future value in 12 years would be twice that present value. And then you'd set up the equation, twice the present value equals the present value, E raised to the K times our doubling time, 12 years, and then solve that. It should solve it. Again, this would be what we did in that first set of notes when we talked about this doubling time. All right, should get the same answer. Should come out to 0.057. All right, we're going to stop this set of notes here. The next set of notes we're going to be starting, so that's actually going to wrap up in uninhibited growth, meaning we can grow indefinitely. That exponential function shoots off and will keep growing faster and faster and faster. The next set of notes, we're going to look at limited growth, where we don't get to grow indefinitely. And these are what's called logistics equations. And so that's what we're going to get to in the next video. The next part of this set of notes is limited growth. All right? And actually, a lot of things tend to be limited growth. And we'll talk about that, like I said, in the next set of notes. So we'll stop that here.